Engineering 305, Chapter 3, Problem 22, which is now what the screen says. Hold on. Magic of television. All right, Engineering 305, Problem 322. The strain components at a point in a body undergoing plane strain are strain in the x direction. Let's see about here. Strain in the x direction is equal to 720 micro. The strain in the y direction is equal to a negative 480 micro, and the shear strain is 360. Shear in xy is equal to, wow, that's really, I got to rewrite that. That's just too sloppy for me. Even for me, minus 480 micro. The shear is 360 micro. And you can put the rads, but radians are dimensionless. Determine the strain components, N in the N direction and the tau in the T direction, the tangential direction, and the shear strain when the NT axes are oriented at 30 degrees clockwise from the NT axis as shown. All right, hold on. So I'm drawing this underneath, but look at that and go, okay, how does that tie up to our definition of theta? How does that tie up? That angle is 30 degrees. Let's get rid of my problem statement. That's 30 degrees, but I don't even want to label that theta. I'm going to label that, that's just our working angle there. Phi is equal to 30. So remember, we measure from X to N in a counterclockwise direction. Right-hand rule from X to Y. So this is theta is equal to, this is important. Going with the sparklies, a negative 30 degrees. And now, we've got theta equal to negative 30. There's our problem right there. That's everything we need to know. Do we have governing equations? Yeah, absolutely we do. There they are. I've got a strain. I'm going to go back to a different color. I've got a strain in the N direction is equal to EX times cosine squared theta plus strain in the Y sine squared theta plus the shear strain sine theta cosine theta, all right? And that's going to be evaluated. So the strain in the N direction is when theta, oh, wrong button, that button, and theta is equal to 30, minus 30. Wow, almost got myself there. You know what? I'm going to write that over. Theta is equal to minus 30. And then if I want to do the strain in the T direction, that's going to be theta equal to 60, or the original theta plus 90 degrees. So that's going to be theta equal to 60. All right. And then I've got to do one more. I've got to do my shear strain transfer. I'm not going to do the math. I'm not going to do all the math. I'm going to tell you that in the N direction you get 264 micro, and in the T direction you get minus 24.1 micro. And then I've got a different equation. Let's shrink this and slide it a little bit. I've got a different equation for the shear. I'm gonna, wow, which one of those do you like? I almost like the double angle one. I'm gonna go with gamma NT is equal to a minus 2 times epsilon x minus epsilon y, sine theta cosine theta, and then a plus gamma. Oh, I was saying double angle, and then I grabbed the other one. But see, I think, and I think this term is the hard term here. This cosine squared theta minus sine squared theta. I think that's the ugly term. I'm going to get rid of that. And you can't even see that I did that. You can't even tell that I wrote that down. I want to go with the other one. Equals minus strain in the x minus strain in the y times sine 2 theta. Okay, that's just 120 degrees. I can punch that in. I can do that math in my head to get me to where I need to go. And then cosine of 2 theta. Again, that's the equation I want to use. And if I do that, that's equal to 1219 micro. Now, we're done. We're done. I mean, I can take my rainbow pen and there's my answer, and I'm all set. But I want to do one more thing, and that is I want to just, does this make sense? And I lassoed that, and then I failed to copy it, and I want to put that right. I want to put that right there. Oh man. And then I'm going to copy over these other answers. Well, I can lasso that and move them. I'm going to copy that. I'll put that there. Undo. Control Z, Control Z. That, and then lastly, the last piece I need to know was my shear. Need a pen. My shear NT is equal to 1219 micro. Now, what I want to do is look at, if I draw, I got to get these equations out of the way. Sorry. Should have done that before. If I draw my normal, then this is 720. This is minus 480. And this is 360. Is that right? 360. All right. And then I redraw this. And I am down. I'm going to down 30 degrees. So I'm going to draw that, and that, and that, and that. And I do that right behind my picture. Slide that over. So now in the minus 30 degree direction, that's 264. And in this direction, it becomes negative 24. And then that and that becomes this 1219. All right. Does that make sense? Does that make sense? If I've got this positive shear, if I just think very briefly about Moore's circle, that's going to be positive. So I'm going to draw my axes, and I don't even care what my zero is. I'm going to go out here and down because that's positive to get to, this is my vertical face or my x-axis. And then I'm going to rotate up in a positive way to get to my principal. Well, I didn't rotate up, I rotated down. So that's going to get me farther away from where I need to go. Now this one's over here. As I go up, that's going to go closer to, that's going to become smaller because this is, this point is 720 and this is minus 480. So this is going closer to 0 because my middle point My middle point is like that. So that as that moves 120 degrees, it's going to get closer to zero. So it makes sense that that is close to zero. That, and then I'm at a point where I'm actually getting a lot of shear. And whether I go up or down, I'm getting a ton of shear. So I we can just think through that, and the Mohr circle will help us go, yeah, that makes sense. Our answers seem like they have the right sign, like we can get that go. Now that's just a bonus. I don't expect that, and we wouldn't do that yet with shear strain, because for shear strain we don't do Mohr circle till the end of the chapter, and this is just the strain transformation. We still have to do principal strains before we get to Mohr circle for strains. Hope you're doing well.